Have you ever been curious about how chatbots like ChatGPT or Copilot operate behind the scenes? Today, we are diving into the world of large language models, also known as LLMs, and uncovering the technology that powers these advanced systems. Let's get started. Imagine a librarian who had read every book in the library and could help you with almost any question. Well, that's what LLM is like, an ultra-smart system that understands and generates text like a human. It's a technology behind many of the chatbots and writing assistants we use today. But how does it work? Let's break it down. LLMs respond in a human-like way by learning language patterns through complex mathematical processes. LLM is trained by feeding it vast amounts of text. Think of it as showing the program countless books, articles, web pages, and so on. This process is called machine learning. By analyzing this massive data, LLM learns about the language, grammar, style, language patterns, relations between words, facts, and even the nuances of different writing styles. Once trained, LLM can predict what comes next in a sentence, respond to questions, or generate text based on the context you provide. Imagine LLM's brain as a giant network of interconnected neurons working together to understand and generate text. Just like the human brain uses neurons to send signals and process information, the neural network is made up of artificial neurons that are arranged in an interconnected layered structure. The type of neural network that LLMs use is known as the transformer model. Think of this as a sophisticated neural network designed to learn from massive amounts of data by recognizing patterns. It consists of multiple layers. These layers include an input layer, several hidden layers, and an output layer. Each layer has a unique role in understanding and processing language. An input layer starts by taking raw text and breaking it down into smaller units called tokens. Tokens can be phrases, individual words, part of words, or even single characters, based on the tokenization system. Since computers work with numbers, these tokens are converted into numerical format that the network can process. So each token is transformed into an embedding, according to the embedding matrix that was produced as a result of model training. An embedding is a vector that represents the token's meaning, and vectors are mathematical representations of objects in space. Imagine the words apple and fruit. After embedding, their vectors will be closer together because they are related semantically, unlike apple and car. This process helps the model grasp the meaning and relationships between words. Importantly, the same word can have different embeddings depending on its context. The middle layers, also known as hidden layers, analyze patterns, grammatical structures, and overall meaning and apply knowledge learned to process input data. The layers in a transformer model can number in hundreds or even thousands, which allows LLMs to grasp everything from basic grammar to semantic relationships, and each layer building on knowledge gained from previous ones. Transformers use self-attention mechanisms to weigh the importance of each token in relation to others. This helps the model understand the context and meaning of the text more effectively than other machine learning approaches. Finally, the output layer generates the model's response, predicting the next word or creating relevant text based on its understanding of the context. It's like how we understand the language, by considering the entire context rather than just individual words. During both training and usage, input data passes through the same neural network layers, though the processes differ. During training, the model learns from data to extract patterns and meanings. During usage, it applies this learned knowledge to analyze new input and generate responses. While LLMs are powerful, they are not perfect. Their reliability depends on the quality of the data they are trained on. If they encounter false information during training, they might generate incorrect responses. Additionally, LLMs can sometimes hallucinate, which means they may produce information that is entirely fabricated when they lack sufficient data to generate an accurate answer. For example, if LLM is trained on outdated medical information, it might give incorrect health advice. It is critical to verify that the information provided by LLMs are from their reliable sources, especially in critical contexts. Large language models can be customized in two main ways: through fine-tuning or retrieval augmented generation, or RAG. Fine-tuning involves additional training of an LLM to adapt to a specific dataset or domain. For example, if a company wants to integrate internal data not included in the initial training, fine-tuning can help. This process does not alter the original or foundation model. Instead, it creates a new instance of the model customized with additional dataset. RAG, on the other hand, is useful for dealing with frequently changing information. It involves creating a knowledge repository that updates regularly. When a user submits a query, RAG fetches relevant data from this repository and combines it with the LLM's processing for accurate and contextually relevant responses without altering the underlying model. Now, let's compare traditional computer programs with LLMs using simple table. Traditional programs follow explicit instructions given in a specific syntax. For example, video games respond to fixed button inputs, and applications have definite user interactions. LLMs, however, are able to handle unpredictable queries, understand and respond to natural human language, providing meaningful answers to unstructured prompts, even those that are outside of the scope of their initial training. If you found this video insightful, please hit the like button and subscribe for more content on AI technology. Also, feel free to drop a comment below if you have any questions or thoughts. See you in my next video.